Hello, this is Group Wolf, and in this video I'll be talking about a part of a project called RSA crypto system, the other part being the McLeese crypto system. First, let me introduce the RSA crypto system. It is one of the first public key crypto systems. It is an asymmetric crypto system, meaning that the public and the private keys are different. You use the public key to encrypt and use the private key to decrypt. And it is based on the practical difficulty of the factorization of the product of two large prime numbers. It is safe and secure because factorization of the product of two large prime numbers, which will be used in our code, is very difficult. It takes a lot of time, and it can be very slow because during encryption and decryption we raise the numbers to a very large power, perhaps. Yeah. It also requires a third party to verify the reliability of the public keys. So here's the key generation. We choose two prime numbers P and Q. We compute the product of the prime numbers, and we compute the lambda n, which is the LCM, the least common multiple of phi p and phi q, with phi being the Euler's torsion function. You can look it up if you're interested. We choose an integer e such that e is between 1 and lambda n, and the greatest common divisor of e and lambda n is 1, which means that e and lambda n are coprime. Then we determine d as the inverse of e under mod lambda n. So e times d mod lambda n is equal to 1. And the key distribution part, the public key is n and e, and the private key is d, p, and q. For encryption, you choose a number m and you raise the m to a power of e, so you get a c, which is the encrypted message. And to decrypt the message, you again raise the c to a power of d, and you'll get the original number. Here is the proof. In order to prove that this code works, we have to show that m to the power ed is equal to m mod pq, which is equivalent to showing that m to the power ed is equal to m mod p, and m to the power ed is equal to m mod q. And a theorem that will help us during the proof is called the Fermat's-Little theorem, and it states that a to the power p minus 1 is equal to 1 mod p for any integer a and prime p not dividing a. So we can start the proof, and since lambda pq is equal to the least common multiple of p minus 1 and q minus 1, ed minus 1 is equal to an integer times p minus 1, or an integer times q minus 1. To show that m to the power ed is equal to m mod p, we have to consider two cases. For the first case, if m is a multiple of p, m to the power ed must be a multiple of p. So m to the power ed mod p must be equal to 0, and which is equal to m mod p. So m to the power ed equals to m mod p. For the second case, in which the m isn't a multiple of p, we use Fermat's-Little theorem. We write m to the power ed as m to the power ed minus 1 times m, and we write the ed minus 1 to become the h times p minus 1. And because of the Fermat's-Little theorem, the m to the power p minus 1 mod p is equal to 1, and 1 to the power h is equal to 1. So m to the power ed is equal to m mod p. And for m to the power ed equals to m mod q, the proof is basically the same. So combining the two proofs for the two cases, med equals to m mod p and med equals to m mod q, we can show that m to the power ed is equal to m mod pq.